This video shows how to represent 3D rotations using unit quaternions instead of rotation matrices. Quaternions power robotics, computer graphics, and aerospace systems because they avoid gimbal lock and compose efficiently. You'll learn to map rotations to the unit sphere, conjugate points by quaternions, and resolve the sign ambiguity with a clean convention. We'll replace each rotation matrix with a unit quaternion living on the 3-sphere. Rotation becomes the sandwich product Q x Q inverse. Since Q and minus Q give the same rotation, we fix a sign convention to make the choice unique. Let's work through it on the diagram. Rotation matrices work, but they have 9 entries tied together by 6 constraints. Quaternions do the same job with just 4 numbers on a sphere. The catch: every rotation has 2 quaternion representatives, Q and minus Q. Without a rule, the encoding is ambiguous. Goals: rewrite the transition with quaternions, then fix the sign so the representative is unique. Step 5. Every rotation matrix corresponds to a unit quaternion on the 3-sphere. Each rotation R sub I in SO3 is represented by a unit quaternion Q sub I on the 3-sphere. A point X in R3 is identified with a pure imaginary quaternion, X1I plus X2J plus X3K. Rotation by Q sub I acts on X by the sandwich product Qx Q inverse. So the transition equation becomes XV at step I plus 1 equals QI times XV at step I times QI inverse plus BI, but there's a subtlety. Q and minus Q give the exact same rotation. Step 6. Both Q and minus Q produce the same rotation. The minus signs cancel in the sandwich, so Q and minus Q rotate every point identically. This makes the quaternion to rotation map a 2-to-1 cover from the 3-sphere onto SO3. To make the representative unique, impose the sign rule: real part of Q sub I is positive. If the real part is 0, the rotation is by exactly pi, and Q sits on the equator. In that case, pick the representative whose first non-zero component is positive. This gives a deterministic choice. Whenever rotations need a compact, smooth parameterization, switch from SO3 to unit quaternions on the 3-sphere, encode the rotation as Q, act by the sandwich product, then collapse the 2-to-1 ambiguity with a sign convention. The transition is now fully quaternionic, with a unique representative pinned down by the positive real part rule.